Thank you. Thank you, Eduardo. Thank you, Inigo, for this invitation. It's always nice to be with the Basque family here. I will just tell you about the invasive and non-invasive brain-computer interface applied to amyotrophic lateral sclerosis, to the advanced stages of amyotrophic lateral sclerosis. I will start where Emmanuel Mandonnet this morning finished. Usually, brain-computer interfaces you have the choice, dependent on the severity and the age of the patient, whether you try to start with a non-invasive brain-computer interface and then move to the invasive one. So I will go from the non-invasive to the invasive one because the majority of completely paralyzed ALS patients are older, and the invasive approach very often cannot be applied because of, of health reasons and problems, infection risk. So I will start with the non-invasive devices, primarily near-infrared spectroscopy and EEG. These are the most used measures. But as you will see, their application is limited, and their efficiency is also highly limited. And later on, Ander will talk about the application of these non-invasive brain-computer interfaces to movement restoration. So I will concentrate on brain-computer interfaces for the restoration or the activation of communication in patients who are completely locked in, who cannot communicate with any other muscles. I always show this, and Grégoire is already tired from this slide. It's a Swiss philosopher, and you may know that Swiss philosophers are pretty rare, but this is a very good one, which most people don't know, but it's translated into Spanish, so you can read it also in Spanish. And one of his statements, and he died in Geneva, and put all his remarks, philosophical remarks, behind him, and when he finished his remarks, he decided to die, and he's there. So in one of his philosophical remarks, he said that losing the capacity for communication is losing life. And you will see that this is, at the beginning, when you hear this for the first time, it sounds like a banality. But, when most of you are clinicians, if you see these patients, then you know that this is not a banality and that without any communication channel, life doesn't make any sense. So I will talk about the completely locked in. It is very important, but virtually impossible to draw a clear line between a locked-in patient and a completely locked-in patient. So we are already questioning, what is a completely locked-in patient in comparison to a locked-in patient? Well, usually you define the lack of eye movements and the lack of application of an eye tracker, which usually you can buy eye tracker and people can communicate with an eye tracker as long as they have some miniature eye movements. So the eye movements have to be higher, larger than 5 microvolts. Otherwise, the usual eye tracker do not work. And so this is a completely locked-in patient. And what you can see, I taped his eyes open, so his eyes are completely paralyzed. In theory, you should test any muscle which is available on the body in order to define a completely locked-in state, because if there's any muscle who is still under voluntary control, by definition, it's not completely locked in. So nobody can do that. You cannot neither as a clinician nor as a researcher, you can look at every single muscle. So we try to look at as many muscles as we can. So this patient, at least for the muscles which are accessible, there's no other movement available. So this is the definition of locked-in state. But please remind, this is not a clear mark between the two states. And in ALS, as you know, it goes slow, usually slow, within weeks, sometimes within months. People move from the locked-in state to the completely locked-in state. So I just point that out because it's a difficulty which we cannot resolve. So this is a non-invasive device. For the non-invasive device, in patients who are fragile, who have a high infection risk, where we cannot use an invasive approach, who are old, or like this one patient, which I'll show you in a second, or they are very young but have other problems, other other medical problems. We use the combination of EEG and near-infrared spectroscopy. And the situation is more or less easy. We usually start with questioning. So we start with questioning, simple questions where we know the answer. Okay, that the computer analyzes the infrared spectroscopy response. The patient thinks yes or no to the question. And with a support vector machine or any other type of machine learning, you try to separate the physiological response between a yes response and a no response. Usually, in these very severe sick patients, we need we have to do this every day. Every day when we start anew, we have to start to do these specific questions. Usually after 20 to 40 questions, we can separate the two. We can separate the response, and then we give them more private questions. Your name is so-and-so, and your past this and so happened. And then if they achieve about 70% separation, then we move to the open question. Of course, with the open question, when you ask an open question, you never know the answer, except you can read the thoughts, which we cannot. So we don't know the answer. We have some means of estimating the answer in the open questions. So this is so we tried in these non-invasive patients. These papers are very controversial. So we got a lot of problems after publicizing some of the papers. Other not. We replicated it, but still, the only conclusion we can draw from these experiments with about 10 completely paralyzed ALS patients is that with non-invasive devices, in most of these cases, you achieve a yes and a no separation. You achieve about 70% correct answers. The moment you move from a yes and no question, in the moment you move like to selection of letters, you want that the patient voluntarily selects a letter, like in an eye tracker. Then, at least in our hands with a non-invasive device, this was never possible in a completely locked-in patient. And we can discuss it wide. I have no answer to that, but it's just an empirical statement. It was not possible in the last 20 years or so since we do this that we can get a patient to voluntary communication, selecting letters and writing words, which are what we usually understand when we say, communication, voluntary communication. The only thing we achieve is yes and no. And I show an example of a young patient here. So this is the usual thing. You record EEG, infrared spectroscopy, and if you have some eye movements left, of course, you always record the eye movements. The eye movements are the most reliable way of selecting a letter or a word from a computer menu, always better than the EEG, always better than near-infrared spectroscopy. And then a patient can answer yes and no. And that's all we can achieve. I give you an example here of questions. I hope you can hear it. So as you can see with your own eyes, the eyes are completely paralyzed. She has a genetic form of amyotrophic lateral sclerosis.
Der Name deiner Mutter ist Margit.
So she gets the question. Now you have to wait 10 seconds. Then she thinks yes or no. The computer tries to separate the answer. Needs time.
Deine Antwort wurde als Ja erkannt.
And it goes on like this. So these are questions where we know the answer. So we can test the validity of the answer. And as I told you, usually you arrive in about 70% correct.
Du hast immer gerne dein Zimmer dekoriert.
You have to wait. People are slow in this state. You can see the eyes are completely paralyzed.
Müsste ja kommen.
Deine Antwort wurde als Ja erkannt.
Okay. So this is another patient over a whole year of questioning. And what you can see, you have about an average of 70%. Of course, there are some sessions, like these sessions, where you get 100% separation. In this case, the patient was in pain. She had a decubitus. She was in pain. We ask her, do you have pain? You get 100% correct answers. So the correctness of the answers depend also on the vital significance of the questions, of course. If it's an important question, the chances that you get a correct answer, like with anybody else, is much higher. Now, we wouldn't do that. None of us would do that if it wouldn't worth it to do it. Now, the quality of life, that's one of the amazing results which we had over the last 30 years about, that the quality of life in those patients who are decided, are ready to go on respiration, that the quality of life in ALS is astonishingly high. So when we look at different groups, what we see here, you see here that there's not a single patient, who is who has a very bad quality of life. So after deciding to go on respiration, and I have to say in family care, quality of life of these people is sufficient and high. Now, when I say this, you have to remember that all the patients I show you and all the patients we see is a positive selection. We have a bias here because these are all people who decided to live. These are all people who have decided to go on respiration. And the 95% who decided to not go on respiration, these 95% you don't see. And I don't see them either. I'm not interested in them because they decided not to live. So we wait until the patient decides, and if there's a rapid decline, then we decide whether brain-computer interface is useful. But then quality of life is good. There's always a significant, when you measure quality of life, there's always a significant difference between the quality of life of the patient and the quality of life of the caretakers. Usually the quality of life of the caretakers is reduced in comparison to the quality of life of the patient themselves. So you better ask the patient themselves and don't rely on the family information. The family information is usually more negative than the patient information. And we have a lot of data. I cannot go into detail, but if you're interested, we can discuss it later. What we showed that how should I say, the emotional tone, the emotional bias in this state, the closer you come to the locked-in state, the emotional bias becomes more positive with progression of the disease. So this is a group of about 30 patients, and what you see here, the red are the patients, and the yellow are the healthy controls. And we presented them emotional slides. And we asked them to rate the emotional valence, positive or negative. And what you can see, and this was replicated several times, what you can see is that the quality of life and the emotional tone in these patients is more in the positive direction than in a negative direction. And that is, of course, correlated with the overall quality of life and a lack of depression. I'm showing you that just because I want to persuade you, and I don't think it's difficult to persuade neurosurgeons about this, that it's worse to do that, and it's worse to try invasive and non-invasive PCIs on those people because the quality of life is so good. Okay, quality of life is also related, as you know, those of you in this morning, or yesterday, I think Conan talked about depression. Of course, one of the hallmark of a bad quality of life is bad sleep. So we look at all these patients. We have all-night recordings. This is one of the patients you saw, the old patient you saw, and you can see they have this is a whole night, and the upper curve is the slow wave activity, and as you know, this is a completely normal sleep pattern, as most of you, except the old ones, like in my age, sleep is pretty bad, but that's aging related. But this is an old patient. It still has a very young sleep, a wonderful sleep. So these patients have excellent sleep recording. They have a normal circadian pattern, and that of course, contributes to the quality of life. Okay. Now, in several publications, I mentioned, I thought that one of the reasons why we cannot get fluent communication, voluntary communication with the BCI, may be related to what Aristotle said about 2,300 years ago. He had the assumption, which was later on studied in the 19th century and was in the 20th century, that thinking, the flexibility and the semantic aspect of thinking, is related to motor capacities and to and motor behavior. So that The motor theory of thinking is an outflow of Aristotelian philosophy. It's not an invention of science, as most things. It's just a consequence, and he thought that the goal-directed movement and the fact that we learn goal-directed movement, that shapes our thinking in that same direction, that shapes our semantics. Now, I believed in that, and I thought if that is true, then long-term motor paralysis should lead to extinction of flexible thinking. And that was my explanation. That was my explanation why it didn't work in these people. Why? I thought, well, yes and no is well. You can answer yes and no reflexively. But the moment you want to create a flexible thought, in that moment, the system is already extinguished because there is no feedback of anything you think. You can think whatever you want. You can think, I want this, I want that, I want this. There's no consequence. So what is the consequence? It's like if you fall in love with somebody and she or he is not responding to you, you kill yourself, if you're Russian, or you give up, which is, of course, the most useful thing, then to try a new one. Okay, so this is what I thought. Now, if this is true, a completely locked-in patient would not be able to communicate flexibly. And now I show you the first patient who's completely locked in, who does communicate flexibly. I was wrong. Thanks to God, I was wrong. Aristoteles is wrong, and everybody after him is wrong. Even after fairly long-term, completely locked-in state, the fact that the motor system is completely, not completely, but more or less completely dead, has no effect on the thought process. Okay, so we had one patient where we implanted the Utah device in the primary and in the primary motor cortex and supplementary motor cortex. Do you know this is the system which was used before in the ALS patient, and you will hear about this from Eduardo and Anda in stroke. It's the same system. We implanted just two. We implanted one in the primary and the second one in the supplementary motor cortex, so they're about 1.5 centimeters apart over the hand region. And this patient, these are the eye movements of this patient. So we had this patient before. He was a young patient. We had him on a non-invasive device, and it didn't work. He was not able to communicate with a non-invasive device. As long as the eye movements were still working, he communicated with the eyes. He used the EEG to help him to communicate. But later on, he was incapable. These are the eye movements before. Look at the scale, you probably cannot see. This is 1 microvolt. So these are minute eye movements. As long as you're 2 to 3 microvolts, the eye tracker is not working with 2 to 3 microvolts. But the BCI works up to 2 to 3 microvolts. But if the eye movement is then dying out, as it did, then here after the second part of the picture, the patient was implanted. The eye movements are 0. So there's no eye movement left. And of course, we test other muscles in the face particularly, whether there's any response there, and there isn't. Okay. So you will see this in a second. Just for you to understand, and with that I finish, each day when the patient starts communicating, we have to find one of these electrodes. Each array has 64 electrodes. So we have to find the electrode of the day, which is the electrode where the patient can use, or the spiking rate where the patient can use to communicate. In order to find this, we use a kind of a Neuro Feedback strategy. So you will hear this in the video. So the patient has himself in an electrode where we saw a good response. The patient has to increase voluntarily the firing rate of that cell and reduce the firing rate of that cell. And he hears it, you will hear it later, and when the tone goes up, that means increase in firing rate. When the tone goes down, that means he has learned to decrease firing rate. And we choose that cell which is able to discriminate then later on for communication. If you want to know how this is working, then you have to ask Jose Carmena later, because his group This is, I will not go into the deep depths of this paper, but this paper and other stuff from Jose explains how this type of neurofeedback, reward-dependent control of brain activity works. And I think this is an excellent example of a perfect scientific explanation of the neurofeedback situation. So then you will hear it in the video, you will hear color names. The patient, and there's another warning here, most patients in advanced ALS stage are half blind or they have compromised vision because the cornea dries out in the course of the disease when the eyes are not moving, and these people see very badly. And this patient sees very badly. So everything is auditory, but of course I have to present it here visually in order for you to understand it. So each letter is a different color. So first we ask the patient, the computer asks the patient color, yellow, green, red, if it's one of these letters, and then the patient hears E, A, D, C, and the moment the right letter appears, he has to increase firing rate of that cell. And with that, he selects it. Okay. How far am I, Eduardo, in time? I'm done? Yeah, a minute, yeah. 5 minutes. Maybe 2. Okay. Here you see, this is the cell, which is it for the neurosurgeons. It's interesting. In the last 3 or 4 months or so, the patient selects always the same electrode in the supplementary motor cortex. So he's not moving. He's not variable in it. The cell which gave him success at the beginning, that's the cell which is the cell which can always discriminate, which he always uses in order to select a letter or a word with a firing rate. So it stays stable, and the other cells are not discriminating between the other electrodes, I should say. Each electrode represents about 3 to 4 cells. Okay, so this is the cell. This is our magic cell number 20, which he uses more or less all the time.
9.
So now he trains. This is a neurofeedback.
9.
So now he learns to control the cell.
Ja.
That was up, firing rate
Der
up.
aktuelle Satz ist
It's
E,
condensed now.
I, gelb.
Now he selects letters. It's a yellow letter, green, wasn't. So it's a green letter.
Ja.
Now the letter come.
9. S.
Now I compress the video. This lasts about half an hour. I cannot bother you with that.
Ja. Der aktuelle Satz ist Bier.
This was the first sentence he said after the implant.
Ja. Der aktuelle Satz ist Bier. Ja. Der aktuelle Satz ist Bierbäumchen da.
Birbäumchen means it's the diminutive from my name.
K.
So he calls me Birbäumchen, like a little tree, a pear tree,
Ja.
small pear tree.
Der aktuelle Satz ist
So that's what you hear usually. Okay. Okay, it goes on and on and on that for hours. Usually he can do this for 1 and 2 hours, and then he's tired, and then we stop it, and we come back on the next day, then you see the same thing. Okay. That's what these people say. There are not many philosophical comments they make. They usually are very concrete. They say what they want. They say the position. They say the pain. They want to have some presence of somebody. These things, very simple things. We expected big philosophical insights about the completely locked-in state, but it's not coming. It's what you would say when you lie on the back for 24 hours a day. And here I give you some example of the quality of life, and then I'm done. Du bist selten müde.
Nein.
So you hear the tone, you can hear the answer.
Du bist oft wach. Ja.
Du bist selten wach.
Nein.
Du denkst viel nach. This is Aristoteles in the back. You can see. I was guided by Aristoteles here.
Du denkst viel nach. Ja.
Oh, he sings a lot.
Du denkst wenig nach.
Nein.
Du bist oft traurig.
Nein.
Du bist selten traurig.
Ja.
So he's in control
Du
of
bist
his
selten
firing rate.
niedergeschlagen.
Ja.
Du bist oft niedergeschlagen.
Okay, it goes on and on like this. Thank you very much. This is the conclusion of what I can say for the invasive thing. We can be really full of hope, particularly the neurosurgeon among us. This is a new and worthwhile application of neurosurgery. Thank you.